The third presentation today brings us back again across the ocean to Europe, where Jack Taggart with Arup is going to talk about the carbon assessment for multi-phase development and a pile testing strategy. Jack, floor is yours.
Thanks, Gerald. Can you confirm you can hear me, please?
Yes, we can.
Excellent. Thank you for inviting me to participate in this webinar series. And thanks for the introduction. I'm Jack Taggart, Senior Engineer at Arup in London. Arup is an independent firm of designers, consultants, architects, advising clients on various complex projects around the world. Today, I have a short presentation on a paper I co-wrote with my colleague, Chris Barker, for the recent DFI conference in Berlin. The title of the paper is Embodied Carbon Assessment for a Multi-Phase Development Pile Testing Strategy. So the paper is presented from an embodied carbon perspective, but really at the center is a value story about strong client relationships, effective planning at early stages of large projects, and of course the results of the study, I think, demonstrate quite well the benefits of those things and how they can influence pile testing strategy and the benefits of pile testing in terms of cost and embodied carbon savings, potential embodied carbon savings. I'm going to give a brief overview of the factors contributing to embodied carbon in board pile foundations and the relatively simple way that we can assess those factors and estimate the embodied carbon within piles and estimate the embodied carbon within the designs that we're producing. I'm going to give a brief overview of the case study where we assess the potential embodied carbon savings additionally alongside the sort of traditional metrics like cost and program when developing the pile testing strategy with the client. And finally, I have a couple of slides on alternatives. So pile testing is not always a viable option, and we recognize that, but there are alternatives. How do we maximize the potential foundation reuse? What benefit do carbon offsetting schemes provide? And how useful are alternative low carbon-free materials for pile foundations? We live in an age of statistics, and there's more and more focus around sustainability, more and more focus around embodied carbon and emissions, particularly in the industry that we work in. One of those statistics, I think, is quite profound. It is that building and construction currently account for around 40% of all energy-related CO2 emissions globally. And as Niall pointed out earlier in his presentation, our contribution on projects generally involves putting large volumes of carbon-heavy materials, steel and concrete, into the ground. So it shouldn't really be a surprise that as designers, engineers, contractors, we do have a responsibility to review standard practices, develop new best practices, help reduce these emissions, and shift this curve left and shape a better world. Before we get too far, there's a few definitions here that I might refer to. Greenhouse gases, I think we're all aware of. CEF is a carbon emission factor. These are factors held in huge databases for various different types of materials and activities to determine an equivalent quantity of carbon. And you can have a look at the other definitions there. So in the UK, the industry follows this whole carbon life cycle, adapted from various standards, 15978 and PAS 2080. There are three main elements. I think they give good context to the assessment process. we have the before use phase, which is typically defined as conception to practical completion, the use stage, the operational life, and then the end of life stage, and beyond. In terms of piles, the embodied carbon for board pile foundation is mainly attributed to factors A1 to A5 in the before use stage, and these are split out into raw material supply, transport of the materials from wherever they're manufactured to wherever they're used, the actual manufacturing, and the construction related emissions. So looking at a typical pile then, rotary board pile by material, concrete typically makes up around 75% of the carbon emissions, with steel responsible for, and steel and wastage responsible for the remaining 25%. I don't think that's surprising. It's also, in any assessment like this, is important to consider the additional items, so any concrete required for a pile cap and the associated embodied carbon, and any pile arisings. What happens in any treatment that's required for those and any disposal of those. So the carbon assessment itself is relatively simple, and I'd like to stress that. I think it's easy to do, so we should be doing more of it. For factors A1 to A3, we just assess the materials by mass or volume and combine those with the appropriate carbon factors, which can be found in various databases. The emissions and carbon equivalent values for the transport of materials is a little difficult. Several assumptions around distance or the mode of transport have to be made and then combined with their carbon factors. Materials can be categorized by region. So for board piles, construction, the construction site and the concrete batching plants are typically relatively close. And for the larger piles, reinforcement cages might be prefabricated and transported by road, rail, water from a bit further away. But for smaller CFA piles, they might be fabricated on site, and the transport of those materials is typically over a shorter distance. So for A5, the emissions arising from site-based works, these include vehicle and plant emissions, materials wastage, although you can allow for materials wastage under factor A1 sometimes. And then we look at fuel, electricity consumption for the various different bits of plant. Now, it's difficult at early stages of projects to make those estimates. So there are various studies. One example from the Royal Institution of Chartered Surveyors in the UK estimate, for example, 1,400 kilograms of CO2 equivalent per £100,000 of project cost. So most of the embodied carbon in concrete board pile is in the concrete, 75% as we've seen. And the amount of embodied carbon in that concrete depends strongly on the cement content. So in the UK, commonly permitted combinations include CEM2B, which is 21 to 35% fly ash, CEM3, 36 to 65% GGBS. So these encouraging the use of cement replacements, which helps reduce the carbon emissions. It's also important to understand that actually for a concrete class, for a given concrete class, the amount of carbon involved may actually vary, sometimes by a factor of 3. So I think this, in our work, we started to engage more with suppliers at earlier parts of earlier stages of the projects and reviewed the environmental product designations to look at exactly how much and determine our own specific carbon equivalent factors for those projects. Moving then on to the case study. This is a project in an area of London where Arup have been involved for over 30 years. And actually many advances in UK piling best practice can be linked in some way back to here. The site itself is a 35 building mixed use development with buildings up to 56 stories. And when we complete this, we expect that over 2,000 rotary board piles and CFA piles will have been constructed. The underlying design approach is relatively simple. It's linked through to these partial factors you can see on the screen, and those partial factors can be reduced as we improve our understanding and reduce our uncertainty of the ground behaviour and the pile behaviour. So our study, and I've included one of the phases of the development as an example with 8 buildings, involves a system that we've developed with the client to understand or estimate the total building load for a given type of a building, depending on the building height, the building type, and the floor plate area. With that, we can estimate, or we can determine a long list of feasible pile types. And you can see on the previous slide. I don't know why it keeps jumping, but with all of those, so then we have sort of 5 or 6 options for each building. It's then easy enough to assign an estimated cost and carbon cost for each of those pile types, and then assess the different numbers of piles or different length of piles required for each of the options, depending on your piled load testing scenario. So this might be, this is no pile testing. We do a preliminary pile test where we load it and understand the failure behavior, or we do a working pile test, one of the contract piles, or we do a combination. So we end up assessing a matrix of over 1,500 different options to inform our pile testing strategy before we've even got going. So at a glance, the results of our study in terms of embodied carbon showed that we could save around 1,000 tons of carbon. And this is a net savings, so it includes the carbon required for the pile test itself, or pile tests. So if we undertook a preliminary pile test or a working pile load test, we'd save around 1,000 tons of carbon, embodied carbon. If we were to undertake both working and preliminary pile tests, we estimated that we'd save around 2,000 tons of embodied carbon. So that's around 2,000 trips to CGeol and back again. In terms of cost then, and I think this helps make the case for the pile testing strategy, we see around a 12 to 15% net cost saving. So that's again including the cost of the pile test for undertaking the preliminary or working pile load tests individually, and a combined 21% net cost saving if we undertake both types of pile tests at different stages of the project. So pretty compelling savings. Now, as I said, I've got just final slides here on alternatives. We should maximise the potential for future reuse where, in all cases, but particularly where preliminary pile testing is an option to save carbon cost. If you don't have to put new piles in the ground at the end of life stage, this significantly helps the overall carbon saving in the grand scheme of things. There are low cement or cement-free materials that are being trialed and more commonly adopted, but these often have links to other carbon heavy industries. So they increase use of GGBS as a cement replacement. GGBS is derived from carbon heavy steel industry with a limited supply. So it's not the end solution. This is just a sort of stopgap. I think the real saving and work that needs to be done around materials is actually engaging with the supply chain at earlier stages of projects, reviewing the EPDs and tracking the EPDs throughout construction so we can refine our carbon factors that we use at the early stages. We're seeing on projects where we are tracking materials consumption and looking at those EPDs, that actually the amount of carbon can vary from those general carbon factors quite significantly. So I think that needs refinement. And finally, on this slide, carbon offsetting. So carbon offsetting schemes are becoming more readily available. It's a growing market for various entities. And we've done some thinking around it, you know, how effective is this? How easy is it to do? And is it a real alternative for developers and owners? Using our study as an example, so for the total 7,800 tons of carbon required for the no pile testing scenario, so that's the total embodied carbon for all the piles we require if we did no pile testing, we need to, or the owner would need to buy carbon offsets equivalent to around 8,000 trees in a reforestation scheme. And those trees, interestingly, would need to live for over 100 years to offset the same amount of carbon. So I'll leave you to think about how effective that is as a solution. So just to bring this to a close, the paper, and I'd encourage you to read it if you haven't already. It gives a brief overview of the factors contributing to carbon emissions. It really shows how simple the assessment is and how easy it is to do and adopt on typical projects. It highlights the value of early stage client engagement, good client relationships, and highlights the potential carbon and cost savings for pile testing. I think that's a challenge we're all quite familiar with. And I expand on some of the discussion around the alternatives that we've just touched on the previous slides. Yeah, and I'll leave it there for today. Thank you.
Thanks, Jack. And thanks for yet another interesting presentation from Arup. I think